Hello and welcome to part 2 on how to create a very simple web framework using Rust. Now in part 1 we created a very simple framework that took an incoming request and dispatched a route handler. In today's video we're going to focus on adding multi-threading to our framework so that we can handle multiple connections. But before we get into that, it's worth spending some time just to fix some of the existing issues the framework has. Now, as I said in part 1, developing a web framework isn't an easy task. There's a lot to consider and there's a lot of issues that we currently have to resolve. So one in particular area is extracting more of the request data. At the moment, we're only extracting the request line from the request data. So let's take a moment to extract the request headers as well as any post data that the request might contain. Now, in the last video, we set up a request type that takes some request data and splits it using the new line characters. But we only split the data once, and as you can see, we're using the split once function, and this will give us a tuple with two elements, where the first element is the request line and the second element is the rest of the data which we're currently ignoring. Now, this data that we're currently ignoring contains request headers as well as any post data. So what we want to do is extract this information and make it available in the request type. And this will make the framework that little bit more usable. So let's start by looking at a sample post request. So here you can see that the HTTP headers are all on individual lines, and then there's a blank line followed by some post data. Now bear in mind that we've already extracted the request line, so the data that we're working with only includes the HTTP headers as well as the post body. So the question now is, how can we extract this data? Well, one of the easiest approaches is to split the data using the new line characters, but the problem with this is that the post data is also going to get split if the post data contains new line characters. But there is a way to solve this problem without the post data being unnecessarily split, and that is to split the data just once using the split once function. And so what this will do is give us a tuple with two string slices, where the first string slice is going to be the first HTTP header and the second string slice will be the rest of the data. And then we can take the rest of the data and then split it using the split once function again, and we can repeat this process up until we get to that empty line. So essentially, when we do the last split, the first str slice should be an empty string and the second str slice should be the rest of the post data. Okay, so now that we have a basic idea on how to do this, let's go back to the Rust code and start implementing this. Okay, so there's a number of ways that we can do this, but the approach that I'm going to take is to use a recursive function where we provide the function with the request data and then we recursively extract the headers and the post data from it. So here I'm creating an extract function that will take the request data as an str slice, but I'm also providing it with a mutatable hash map so that we can store the headers as key value pairs. Okay, so now what we want to do is split the request data using the new line characters, and we're going to split the data just once using the split once function. And this of course will give us an option with a tuple. So we can use if let sum to extract that value, and what we should end up with is a tuple with two string slices. And in this case, I'm simply destructuring the tuple so that we end up with two elements where each element is bound to a variable. So now what we need to do is test if the header line is an empty string, because remember, as I said, we're going to recursively go through the request data. So therefore, at some point, header line will be an empty string. And if it is an empty string, then we know that we processed all the request headers and we can stop the recursion. And anything that comes after the empty line, we know that it could be potentially post data. For now though, I'm going to add a comment here so that we know that we need to handle the post data here. Now in the else block of this if statement, we know that the header line is a request header which consists of a key and a value separated by a colon. So to extract this key value pair, we can once again use a split once function, but this time split it using the colon character, which of course will give us a key and a value which we can then insert into the hash map. Now for the purpose of code readability, I'm using the unwrap function here. So this will give us a tuple with two elements where the first element is the key and the second element is the value. And now we can go ahead and create an entry in the headers hash map table using the key value tuple. Now notice we're using the toString function on the string slices, and this is because we've set up the hash map to be of type string, and this is purely just to avoid lifetimes. So at this point, we've extracted the key value from the header line, and we know that the header line isn't empty, so we know that there's more headers to come. So we can call the extract function again, but this time we can provide it with the rest of the data. And remember that the rest of the data doesn't include what's already been extracted. So by calling the extract function recursively, we can extract all the request headers, and when we get to that empty line, then the recursion should stop. Okay, so now we have a partially completed extract function where we can extract request headers, and we'll get back to this function a little later on so that we can extract the request body. But for now, let's go ahead and test what we have so far. But before we do any testing, we need to call the extract function for the first time. So here I'm creating a hash map so that we can pass to the extract function, and then later we'll print it to verify that it actually contains request headers. Now when we call the extract function, we need to pass the request data where the request line has already been extracted, and this data is currently in the rest variable which we are currently ignoring. Okay, so now let's test what we have so far by printing the headers hash map, and we'll do a simple test where we issue a post request with a post body and see what the outcome is. So here we have a sample post request with a JSON post body and a content type. Now let's execute this request and see what gets printed to the terminal. Okay, so it looks like the extract function is working fine. So we now have a hash map with request headers, but looking at the value field, I can see that there's a trailing space, but we can remove that using the trim function. Okay, so the last thing that we want to do now is extract the request body. So let's go back to the code and make some changes. So to extract the post body, we just have to make a few changes to the extract function. So the first thing that I'm going to do is create a mutatable string and pass that to the extract function. And this string will store the post body. So we're taking the same approach as we did with the request headers. Now the value of this string is going to be set in the if statement where we're checking if the header line is empty. And we know that when the header line is empty, everything that follows afterwards is the post body. Okay, so now the extract function is complete and we're able to extract the request headers as well as the post body. But we need to expose these data to the request type so that we can make use of them in the root handlers. So to do this, we can create two fields on the request type, a headers field and a post body field. And then when we return self, we can go ahead and populate these fields using the data that we've extracted. Now, because we're developing a zero dependency framework, we don't have the option of using a library like Serde to deserialize the post data to a JSON object. So by exposing the raw post data, we can leave it up to the user of the framework to use whatever library that they want. And this also helps us to avoid dependencies, and in a cheeky way, we don't have to write XML or JSON parsers. Okay, so before we move on to threading, which I said was going to be the main part of this video, and I've already spent about 6 minutes doing this, let's go ahead and print the request headers as well as the post body in one of the root handlers. So now if we execute this request, what we should see in the terminal is the headers as well as the post body. Okay, so now we have a very basic request type that at the very least we can use to get some information about the client request, but there's still a few things that's missing. We haven't yet passed the query strings. For now though, let's move on and make this framework multi-threaded so that we can process multiple client connections concurrently. Okay, so there's two different approaches that we'll take a look at. The first is to have each connection handled by its own thread. Now this isn't an ideal solution, but we'll write the code anyway and then test it using a tool like WRK. And then we'll go ahead and write a very basic thread pool where we have a limited number of threads that can handle all of the connections. So let's start by bringing in the thread module and the archetype into scope. And we're going to need the archetype so that we can have shared ownership of data across multiple threads. Now let's go ahead and create a thread and move the handle connection function into that thread. But unfortunately, it's not that easy because as you can see, we have this error. So basically what's happened here is that the closure provided to the spawn function is trying to take ownership of self, and this is not what we want. So let me see if I can explain this a little bit better. Imagine if we have two client connections and the first client connection creates a thread and then self gets moved into that thread. And then the second client connection also creates a thread and tries to move self, but self was previously moved into the first thread. So this is why Rust won't allow this. So to solve this, we're going to use the archetype. And so essentially what we're going to do is move roots out of self and put it into an arc. And then we can clone the arc and move the clone into the thread. So essentially every thread is going to have its own clone. Now, just to clarify, when we clone the arc, we're not actually cloning the data that the arc owns. It's the arc handle that's being cloned. Okay, so now we can pass the roots clone to the handle connection function, but this is going to cause another error because the handle connection function currently takes a reference to a vector of root. But thankfully, this is a short-lived error and all we have to do is update the handle connection function. But this does leave us with another error, and that is roots is no longer a vector, it's an arc, and arc doesn't implement the into-iterator trait. But the arc type does implement the deref trait, which means we can call the vector's iter function and use that to iterate over the roots. And now no more errors, so let's do some testing, but before we do that, let's print the current thread ID for each of those threads so that we can see that a different thread ID is actually being used. Okay, so now let's test the server, and I'm going to use a command line tool called walk or WRK to test how many requests per second we can achieve. Now this isn't an exact science, but we'll go with the value that is given us, which is about 10k requests per second. And if we take a look at the server's console log, we can confirm that a new thread has actually been created for every client. Okay, so with that 10k requests per second in mind, let's go ahead and implement a basic thread pool, and then we can run the WRK command again and then compare the results of the two different approaches. Okay, so to create the thread pool, we're going to spawn threads using a for loop, and for now we're going to keep the iteration count down to 2 so that we only spawn 2 threads. Now one thing to note here is that we're creating these threads before receiving any client connections, so these threads need to be active for the entire duration of the program. But at the moment, these threads will spawn and then die immediately, so to keep them alive, we're going to use a loop. Okay, so now we have two threads that are ready and waiting, and the next stage is to call the handle connection function from within the loop. But the issue here is that the handle connection function takes a TCP stream, but at the point of creating the threads, we don't have access to a TCP stream. So to solve this, we need to use an MPSC channel. Now, an MPSC channel is formed of two parts, a sender and a receiver. So we can use the sender to send a TCP stream from the main thread back to one of the spawned threads. And these threads will have access to a receiver so that they can receive a TCP stream. So you can think of a channel as a way to pass data from one thread to another. But we only have the one receiver and two threads that need access to it. So we'll need to clone the receiver and then pass the cloned instance to each of the threads. Now, when we clone the receiver, we have to do it in the for loop so that we can have one receiver for each of the spawned threads. And now we can go ahead and move the RX clone into the thread and then call its receive function to receive a TCP stream that's been sent from the main thread. Okay, so now Rust doesn't like this code, so let's take a look at the error message and see why that is. So the error is telling us that the receiver TCP stream can't be shared between threads safely, and that's because it doesn't implement the sync trait. So essentially, if a type doesn't implement the sync trait, then references of that type can't be shared between threads safely. So in this case, let's take a moment to understand why that is. So imagine for a moment that the receiver has some internal state like a queue, and then calling the receive function dequeues an item, thereby mutating the queue. Now, if two threads had access to this receiver and they both called the receive function, then they'd both be racing towards mutating this internal queue. Now, this queue doesn't provide any internal synchronization, so it's up to us to implement something that will allow only one thread to mutate the receiver at a time. So to fix this error, we need to put the receiver into a mutex and then put the mutex into an arc. So essentially, using the arc, we can get clones of the mutex, but the mutex itself will guard the receiver from being mutated by multiple threads at the same time. Okay, so now we have a TCP stream, but we also need the vector of roots because these are the two arguments that we need to provide to the handle connection function. So just like before, we need to clone the roots using the arc and then move the clone into the thread. But this time we need to clone the roots again within the loop, and that's because the handle connection function takes ownership of the roots. So when the loop iterates again, we need to get a new clone. And now we have the two arguments that we need to pass to the handle connection function. So with that, we've just completed a very basic thread pool. But before we start testing, let's print the thread ID to confirm that only two threads are active. Now with the same parameters as before, let's test the server and hopefully we should get more requests per second just using two threads. So as you can see, we're getting about 14,000 requests per second, but this value relates to each of the threads being used to carry out this test. So the total number of requests per second is actually 27,000. So that's almost like a 50% increase than the previous test. And here in the server's console log, we can confirm that only two threads have been used. Now at the moment, we're only using two threads to handle the connections. So let's see what would happen if we increase the threads to 4. So the results seem the same as when we had two threads running. So just by increasing the number of threads doesn't necessarily mean we'll get more requests per second. Okay, so now we've come to the end of this video and I hope you enjoyed it. And if you did, please consider giving it a like and I'll see you all on the next video.